Hello. Well, it's time to finish up Module 2, and we're in the third part of it now. We've already looked at categorical variables and quantitative variables and tables and graphs that you can use to depict them. And now it's time to talk a little bit about two variables. Many times researchers are interested in the relationship between two variables, and there are both some tabular and graphical approaches that can be used to handle two variables. On the tabular side, we're going to look at something called a cross-tabulation. On the graphical side, we're going to look at scatter diagrams and stacked or side-by-side bar charts. Let's start with the cross-tabulation. It's basically a table that's going to show us two variables simultaneously. The variables can be either categorical, quantitative, or a mixture of the two. Let's do an example to illustrate. Supposing I took a sample of 500 people and I've broken them down into two different variables. One is their political preference. We have Democrats, Republicans, and Independents. So we had a total of 250 Democrats, 200 Republicans, and 50 Independents. And the other variable is their income range. Let's say we've broken income down into two ranges, less than or equal to 100,000 or greater than 100,000. We had 400 people with an income less than or equal to 100,000, 100 people with an income above 100,000. The inside boxes give us what I sometimes call the joint frequency of these two variables. In other words, for example, we have 200 people here who were both Democrat and were in the income range less than or equal to 100,000. We had 50 people who were both Democrat and in the income range above 100,000, and so on. In a sense, what we're getting here is we basically have two frequency distributions built into one. Vertically, we have the political preference frequency distribution. Horizontally, we have the income variable frequency distribution. Let's go back and take a look at that. Horizontally here, we have the frequency distribution for the income range, 400 people in this category, 100 people there. And vertically, we have the frequency distribution for the other variable, 250 Democrats, 200 Republicans, and 50 Independents. Later in the course, we're going to be using tables like this, especially when we get to the probability material, and we will find them somewhat helpful in solving probability problems. Okay, now let's go to some graphical techniques that can be used to display two variables. One of the simplest is called a scatter diagram. In fact, many of you have probably drawn scatter diagrams in your life back in math courses. A scatter diagram is used to look at the relationship between two quantitative variables. One variable will go on the horizontal axis and one on the vertical axis. And you simply plot your points. That is, we have a sample of observations on the two variables. You simply plot your points to represent the diagram. In many cases, we put a trend line through the points, where the trend line can be shows the general pattern of relationship between the variables. Here's some examples of trend lines. This comes from a website, emathzone.com. They give you 4 examples here. All the dots just represent the different points that have been plotted, and we put a trend line through it. We obviously here have an upward sloping or positively sloped relationship, and it appears to be fairly linear, fairly straight line. Just the opposite over here, now we have a downward sloping straight line relationship. Here we have a negative relationship, but it seems to be curved or nonlinear. And finally, down here, we pretty much have no obvious relationship. No linear relationship, no curved relationship. Let's do an example. Let's go back to our Music Mania company. Suppose they run a special sale on weekends, and prior to the sale, they run some radio commercials. For the past 6 sales, let's say they've gathered some data on their sales in thousands and the number of commercials they ran. We're going to let Y be the sales variable and X be the number of commercials. If you just look at the data points here, you can generally see a relationship. You should be able to see that the smaller X values, 4 and 5 for example, generally are associated with lower Y values, and the larger X values are associated with larger Y values, which is basically going to tell you that when we graph this, you're going to get an upward sloping relationship. So if you simply plot those points, you will get the following trend line. Sales again on the vertical axis, the number of radio ads on the horizontal axis. Just plot the points, put a trend line through it, and we can see an upward sloping or positive relationship. Okay, a couple of other things that we can use to represent two variables. We can go back to bar charts and modify them somewhat. One thing that we can do is what's called a side-by-side bar chart, which will allow us to show two bar charts on the same graph. Each group of bars is going to represent one value of one of the variables, and each bar within the group represents a value of the other variable. Let's go back to our political preference and income data and do a side-by-side bar chart. And it will look something like this. Remember, we had three political preferences: Democrats, Republicans, and Independents. Each bar within the group then represents one of the values of the other variable, the income variable. The blue bars represent those people less than or equal to 100,000 in income, and the purple bars, those above 100,000. So within the Democrats, if you go back to the original data, we had 200 Democrats who had an income less than or equal to 100,000, and 50 Democrats who had an income above 100,000. For Republicans, we had 175,000 with an income below 100,000, and 25 Republicans with an income above 100,000. And with the independents, we had 25 in each category, 25 below 100,000 and 25 above 100,000. So that's called a side-by-side bar chart and gives us a fairly easy way of putting two variables on the same graph. Again, it's a frequency bar chart because I'm measuring frequencies on the vertical axis. An alternative to a side-by-side bar chart is what's called a stacked bar chart. Here we'll just put the bars together or stack them on top of one another and use different colors to represent the values of the different variables. Again, the same example that we've used before, the political preference and income variables. If you go back to the original data, you remember that we had 250 Democrats, and we simply used different colors to break out the two income components. Again, the blue area is those with incomes less than or equal to 100,000, 200 of them, and the other 50 with incomes above 100,000. And in a similar way, Republicans and Independents. It's kind of important on stacked bar charts and on side-by-side bar charts to make sure you use distinct colors so it's easy to read. But you'll see these quite often again in magazines and newspapers as a way of putting two variables on the same graph. Okay, I'm going to finish off the graphical material with a little bit of information here on bad graphs. The graphs can be very useful. They can do wonderful things and show us a lot of good information, but they can also be drawn very poorly. Watch out for the following as I note here. Axes must be labeled properly. Especially with bar charts, make sure that you only vary the height and not the width. Varying both can give the wrong impression. And always watch out for scaling on the axes. Make sure that the axes are properly labeled and have numbers or labels to them so that you can understand what values are on both of the axes. Let's take a look at an example. Here's a website that has some nice examples of bad graphs. What we'll call misleading graphs. Take a look at this bar chart here, which shows average house prices in 1998 and 1999. If you take a close look at the graph, you should be able to see something wrong with it. Certainly it looks like the bar on the right, 1999, is about 3 times as high as the bar on the left. But look at the numbers. This distance represents 80,000, yet the same distance now only gets you up to 81, and the same distance to 82. So they changed the scaling of this axis, which gives a very misleading impression. It looks like housing prices in 99 were 3 times as high as 98, but they certainly were not. Here's the way the bar chart should have looked, with the two bars almost equal in height. Here's another example. Take a close look at this graph, see if you can find something wrong with it. Give you a second or two here. Actually, there's two things wrong with this graph. First one that's wrong, notice you've got numbers on the axes, but nothing that tells you what those variables are. You have no idea what you're measuring horizontally or vertically here, which makes it a pretty worthless graph. You'll also notice if you look at the scaling here, if this is 1 unit, this is 1 unit, suddenly the same distance is 2 units, then 4, then 8. Once again, they've changed the scaling on the vertical axis. And they let you know that here in the answer. Here's a third example. This is what's sometimes called a three-dimensional bar chart, where you kind of give the representation not only of height and width, but you also give a visual representation of depth by turning the graph sideways somewhat. Again, there's a couple things wrong with this bar chart. You've got something on the vertical axis here labeled number of singles sold, but there's no numbers on that axis. So there'll be no way of knowing what these measurements are. The other thing is because of the three-dimensional effect, it probably looks like the orangish reddish bar here in front. I guess I'll call it red. It probably looks like that bar is larger than all the others. But actually, in terms of height, it's no taller than the blue rectangle here. In other words, the 95 and 97 values are really the same. If we reveal the answer here, this is what the bar chart should have looked like if you didn't use that three-dimensional effect and if you properly scaled the axis. Finally, one last example. Again, in most textbooks, we like to use bar charts, rectangles of equal width, and only vary the height. But many times magazines and newspapers like to use different kinds of pictures. For example, here they're representing the number of people who own different types of pets. So here's the people who own the dogs, here's the people who own the cats, the horses, and other things. And they give you a little key. They tell you that, one dog equals 50 people who own them, one cat is 50 people, etc. And then they give you this graph. Here's the dog owners, the cat owners, the horse owners, and others. Again, what's wrong with this graph? Well, you can see if you count the number of cats here, 1, 2, 3, 4, 5, 6, 7, and each one represents 50 owners, that's 350 cat owners. Yet here there's only 3 horses here, so that's 150 people. But they've taken this row out much farther, and it looks like that, just visually, it looks like more people have horses than cats or dogs. Once again, they should have graphed it differently. It should have looked more like this. If here's 3 horses, you make the horizontal distance here the same as 3 cats or 3 dogs to make it equivalent. That is, if you insist on using pictures of horses and cats and dogs. Okay, so those are a few things that are incorrect with graphs. I have one other thing here. Let's go back to Ronald Reagan as president. Over here, was giving a speech one night about taxes, and he used this graph. I know it's a little hard to see in the distance here, but he was comparing their bill to somebody else's bill. I would assume their bill means the Democrats' bill, and our bill is the Republican bill. And so he drew this graph that shows this big gap in what your taxes are going to be based on whether or not we pass their bill or our bill. Again, the big problem with this graph is notice the vertical axis. There's just a big dollar sign there. There's absolutely no numbers. Without numbers, it's impossible to tell how big that gap really is. It could be large, it could be very small. So again, always look for things to be properly labeled on both the horizontal and vertical axis. And that is the end of Module 2.